this lecture, we have seen the properties of light called as an interference of light. Now in this session, we have to define what do you mean by diffraction of light. You know that light travel in a straight line path. When obstacle is placed in its path, then what happens? Its shadow is produced. Okay. Therefore, the bending of light near the edges of an obstacle and enter this light rays into the region of geometrical shadow is called as diffraction of light. It is common for all the types of waves. You are familiar with the sound waves. We can hear someone talking even though there are some obstacles. भिंतीच्या पलीकडे जर कोणी बोलत असेल तर ते आपल्याला ऐकू येते. तिथं भिंत ही ऑब्स्टॅकल आहे म्हणून ते आपल्याला ऐकू येत नाही असं नाही. तसंच लाईट रेज सुद्धा लाईट रेजच्या मध्ये जर कोणी ऑब्स्टॅकल्स आलं तरी सुद्धा काय होतंय की लाईट रेज हा बरोबर त्या ऑब्स्टॅकलच्या एजेसला काय होतोय बेंड होतोय आणि इट प्रोड्युसेस इट्स जॉमेट्रिकल शॅडो. दिस इज कॉल्ड एज अ डिफ्रॅक्शन ऑफ लाईट. Let us see this again. What do you mean by diffraction of light? The bending of light around the edges of an obstacle and enters the light into the region of geometrical shadow is called as a diffraction of light. The condition for diffraction of light is the size of obstacle or slit should be small as compared to the wavelength of light. There are two types of diffraction, Fraunhofer diffraction and second is Fresnel diffraction. Then what is Fraunhofer diffraction? The diffraction in which source of light and screen are at an infinite distance from obstacles is called as Fraunhofer diffraction. Diffraction pattern हा कधी तयार होणार आहे? ज्यावेळेस सोर्स पाहिजे, नंतर ऑब्स्टॅकल्स आणि नंतर काय पाहिजे स्क्रीन पाहिजे. म्हणजे सोर्स आणि स्क्रीनच्या मध्ये काय पाहिजे ऑब्स्टॅकल्स पाहिजे तरच डिफ्रॅक्शन पॅटर्न हा तयार होणार आहे. मग फ्रॉनहोफर डिफ्रॅक्शन्स मध्ये ऑब्स्टॅकल पासून सोर्सचं अंतर आणि ऑब्स्टॅकल पासून स्क्रीनचं अंतर हे कसं असतं इन्फानाइट असतं. ओके. देन द वेवफ्रंट हियर is nothing but a plain wavefront. In order to obtain the Fraunhofer diffraction, we have to use the plain wavefront. Second type is Fresnel diffraction. The diffraction in which source of light and screen are at a finite distance from the obstacle is called as a Fresnel diffraction. The incident wavefront is spherical wavefront or cylindrical wavefront. तिन्ही टाइप्स आपण वेवफ्रंटचे पाहिलेले आहेत. प्लेन वेवफ्रंट, सिलेंड्रिकल वेवफ्रंट and a spherical wavefront. Okay. Now next point is Fraunhofer diffraction due to a single slit. Then in this ray diagram, what is AB? AB is the slit. The width of that slit is small a. Then near the slit there is a convex lens. Due to this convex lens, all the rays, secondary rays of course, it is focused at one particular point on the screen. Therefore, in Fraunhofer diffraction, we have to use the convex lens. Then screen is placed at a sufficient large distance from the slit. The distance between slit and screen is capital D. This D is very greater than that of the A. D should be the 10 meter and small a means width of the slit should be the 10 raised to minus 4 meter to the 10 raised to minus 3 meter. Therefore, it is very small. जरी आपण इथं दाखवलंय पुष्कळ अंतर, हे डिस्टन्स भरपूर दाखवलेलं आहे, परंतु ऍक्च्युअल ते प्रॅक्टिकल सेटअप मध्ये काय असणार आहे, इट इज व्हेरी स्मॉल. ओके, नाउ in experimental arrangement, what is this? AB is nothing but a width of the slit. Then parallel beam of light, of course monochromatic light, is incident on the slit AB. Then this slit AB can be divided into the number of slits, that is slits element. Therefore, each slit element produces the secondary source of light and it produces the diffraction pattern on the screen. Okay, figure shows the two sets of the parallel rays. This is one set of the parallel rays which is meet at P0 and this is the other set of a parallel rays which is meet at the P. Okay, then what happens? See this. First we see this set of the parallel rays. The secondary rays traveling in the directions parallel to the OP0 come to focus at a P0. See this. This rays again B पासून जो काही secondary rays produce झालेले आहेत, these rays they are parallel to the OP0 and it will produces the bright point at a P0 because the path difference is 0. As the path difference is 0, both these waves are in the same phase. Therefore, at point P0, this P0 point will appear as a bright point and constructive interference is obtained at the P0 on the screen. Then what about P? Point P will be of minimum or maximum intensity. It's depending upon the path difference. See this, another parallel set of the rays. Okay, this is AP, this is nothing but a BP. Path difference is nothing but a BC. या वेव्स ने किती अंतर काढलेलं आहे, जो काही पाथ डिफरन्स आहे त्यांच्यामधला किती आहे, BC एवढा आहे. BC जर डिस्टन्स आपल्याला कॅल्क्युलेट करायचं असेल तर वी हॅव टू यूज दिस ट्रायंगल, right angle triangle A, B and C. In this triangle, what is the value of sin theta? Sin theta is equal to the BC upon AB and which is equal to the BC. AB is nothing but A. Therefore, BC is equal to the A sin theta and which is equal to the path difference, which is equal to the lambda. Therefore, we get the equation path difference is equal to the BC is equal to the A sin theta is equal to the lambda. If the lambda is the path difference, then point P will appear as a dark point and destructive interference is obtained at point P. Okay, so another side ला जर आपण इथे point P consider केला तर again P will appear as a dark point and destructive interference is obtained on these sides also. If K is the midpoint of AC, AC ला जर आपण K हा midpoint find out केला किंवा consider केला तर what about OK? OK is nothing but a 1/2 of BC and therefore OK is equal to the 1/2. BC is nothing but a lambda, then it is equal to the lambda by 2. Therefore, path difference between AP and OP is the lambda by 2. As a result, destructive interference is obtained at point P. Therefore, consider any such pair of points which is equidistant from A and O. A आणि O पासून कोणताही पॉइंट जर इक्विडिस्टन्स वर आपण कन्सिडर केला तर त्याचा सुद्धा पाथ डिफरन्स किती येणार आहे, लॅम्बडा बाय 2 येणार आहे. देयरफॉर लॅम्बडा बाय 2 प्लस लॅम्बडा बाय 2 अगेन वी गेट द लॅम्बडा. ओके, देयरफॉर BC is equal to the A sin theta is equal to the lambda. This equation पहा, A sin theta is equal to the n lambda. This is the position of nth minima. This is the position of n minima. Okay. And a sin theta is equal to the 2n plus 1 lambda by 2. This is the position of nth maxima. All these two conditions are very important. A sin theta is equal to n lambda. This is the condition for nth minima. A sin theta is equal to the 2n plus 1 lambda by 2. This is the condition for nth maxima. म्हणजे ओव्हरऑल डिफ्रॅक्शन पॅटर्न मध्ये काय असणार आहे, सेंट्रल पॉइंटला तुम्हाला मॅक्झिमम इंटेन्सिटी मिळणार आहे आणि नंतर इंटेन्सिटी विल गोज ऑन decreasing. If you see the diffractions pattern, then pattern is like this. Central intensity is higher and then intensity goes on decreasing on these sides and on these sides also. Here is the central maxima, which is nothing but a P0. Here is nothing but a P and here is nothing but a P. Okay, distance between them is nothing but a Y. This is Y. Therefore it is 2y. This is the width of the central bright band म्हटलं तरी चालेल. Okay. This is all about the Fraunhofer diffraction due to the single slit. हे दोन पॉइंट्स याच्यामध्ये महत्त्वाचे आहेत. This is the condition for nth minima. A sin theta is equal to n lambda. This is the condition for nth maxima. A sin theta is equal to the 2n plus 1 lambda by 2, where lambda is the wavelength of light. Okay, let us stop here.